Hello, so in this video we will talk about finite state automata and its application as a language recognition machine. So let's start with the definition. So we have a finite state automaton, which is a singular form of automata, is defined as the following. So it has a set of states, which is S. It has an input alphabet, which is I. It has a mapping for each pair of set and input for to the next state. So we have a previous state and given input, we can find the next state through the mapping F. Okay, and then we have a starting symbol, and then we have a finite set of final states. Okay. That final states is obviously a subset of our total number of states, okay, or total states. And in other words, the only difference between this and a finite state machine is what? There is no output. Okay. Okay. So a deterministic finite state machine is what? So a deterministic finite state machine is that we have a unique next state for every input state pair. And if that is not the case, then we have a non-deterministic finite state automaton. Okay. Okay, now we talk about language recognition. So let's see what is the definition. So we say a word or string is said to be accepted or recognized by a finite state automaton if it is possible to start at S0 and traverse the path of the string to stop at a final state. Okay. A language is said to be recognized by a finite state machine if it recognizes all the strings in that language. So for example, if we have a finite state machine, which is very simple, it's finite state machine. This is S0, this is S1. Okay, so and this goes to 0 here and 1 here and 0 here and 1 here. Okay, so for this finite state automaton, the string 0 is recognized. Why? Because we can start with S0 and traverse this path just 0 and end up at a final state. So this means 0 is recognized. Okay, now if we find all the strings which are recognized by this finite state automaton, then we have a language. So then a set of all strings which are recognizable by a finite state automaton is the language. Okay, so this is what is written here. A language is said to be recognized by a finite state automaton if it recognizes all the strings in that language. Okay. Okay, so now there are two kinds of problems which are encountered, mainly two kinds of problem in the start. So then we have identifying the language for a given finite state automaton. So this means that we are given a finite state automaton and we want to find what is the language that is recognized by that. The inverse problem is that we are given a language and we have to design a finite state automaton. Okay, so let's now focus on the first one. Okay, so now we will say 1 here, 1 because of this one. Okay, so now let us say we have a finite state automaton which looks like this. Okay, so this is the finite state automaton we have, and we want to see what kind of language it generates. Okay. Okay, so now let's write down all the strings which we can find which it can accept. Okay, first of all, it can accept just 1 because we can start with S0, take just 1 and end up at ending state. Then that ending state S1 has a self loop to itself with an input of 1, which means I can go 1 and any number of 1s I can have 1 1 1 1 1 1 1 1 1 and so on. Okay. Okay, now I can also have 0 0 1 and then 0 1 1 because of the same story which we talked about before, and so on. Okay, but then I can also have 0 0 and then 0 1 1 and so on. So 0 0 0 sorry, I should not say 0, right? So this is 0 1 0 1 1 0 1 1 1, so and so on. Okay, now note that, so this means what happens if a 0 comes at here at S1, that we can't reach S1. So this state, once if we reach S2, we cannot reach an ending state. So we don't have to worry about this when we talk about the generation of a language. So we have either 1 1, then 2 1, 3 1. So we can say 1 to the m. So m is greater than or equal to 1. Then we can have 0 0 0 0 0 0 and so on. Okay, but we can also have no zeros, right? So then we can say 0 to n, and here I can say n greater than 0. Okay, so this is the string. So remember, 0 to the n means n zeros followed by m ones. So we can have any number of zeros followed by any number of ones, provided that this n is greater than or equal to 0 and this m is greater than or equal to 1. Okay, so typically what we do is we write it in set builder notation. So we say 0 n 1 to the m such that, okay, so this is one way to write it. Okay, now let's try the inverse problem. Now let's say we have a problem that we want to design. So we say design a deterministic finite state automaton that recognizes all strings, all bit strings, for example, with exactly 3 zeros. Okay, so now what is my strategy? So our strategy, what is our strategy? So our strategy is we need some states which can remember how many zeros have been collected in the bit string so far. Okay, so then as usual we start with S0. Okay, and then we have S1, and we go from S0 to S1 if there is a 0. So S1 is a state which remembers that we had only 1 0 so far. Okay, and then for 1 we say, okay, 1 we stay here, and here we say 0 to S2. Now S2 is the state which remembers that there have been 2 zeros so far, and for 1 we still stay, and then for S3, remember S3 is where we get 3 zeros, right? So this is a 0 0 0 and is an acceptable string in the language we want. So this means S3 has to be the final state. Okay, and also for 1 is still good because S3 remembers that there have been 3 zeros so far. Okay, now what happens when we get a 0 here? Remember, when we get 4 zeros, then we don't want that to be in the language, correct? So we define another state and we say, if we have a 0 here, we go to a state S4 from which we can never come to the final state, and then we say, okay, whatever happens here, we can stay here. So now we can say that 1 1 1 0 1 1 1 1 0 1 1 1 1 and then 0. So the moment we get the third 0, we are in our final state. After that, any number of ones can come because the number of zeros are still 3. But the moment we get another 0, then we get to a state where the language is never recognized by that final state at automaton. So these two are very simple examples. Note that, I mean, sometimes we have to think a lot for this design problem. Okay, and similarly, the forward problem of finding the language can also be a little bit tricky. If for example we ended up writing a pattern out of our set of languages, sometimes it's possible, sometimes it cannot be possible. So even if we just write the set of strings we observe from the finite state automaton, that's still good enough. Okay. Okay, so this is it for the introduction of finite state automaton and how can we relate language recognition to this concept. And specifically we talked about deterministic finite state automaton, where we can see that for each set of states and input we have a unique final state. Okay, so this is it for this video. Thanks for watching and hope you like the video.